Yay. Okay. All right, you guys, here we go. We got more simple harmonic motion. This is a pendulum, okay? What you're seeing here is a pendulum. And believe it or not, this is an example of simple harmonic motion. So maybe I should raise it. I feel this need to convince you of that fact. So I'm going to convince you in 3 ways. Number 1, I'm going to show you a video that shows that the motion of a pendulum tracks with uniform circular motion, just like the spring mass system did. And so that means it's going to be simple harmonic motion. Then I'm going to actually give you a displacement versus time graph of the pendulum, and you'll see that that's a sine wave or a cosine wave, and that's further proof that this is simple harmonic motion. And then finally I'm going to show you math and demonstrate that the restoring torque is proportional to the angular displacement, which again is one of the attributes of simple harmonic motion. Restoring force proportional to the displacement. Well, with a pendulum, the restoring torque is proportional to the angular displacement. So after those 3 things that happen, you will be utterly convinced that a pendulum is simple harmonic motion. Let's go ahead and do the video first that shows uniform circular motion tracking with simple harmonic motion. The Video Encyclopedia of Physics demonstration. Okay, here we go.
This rotating disc and this pendulum will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed. If we start the pendulum swinging, just as the spot passes the pendulum stays in a vertical line with the spot.
So do you believe that a pendulum is simple harmonic motion? Not yet, huh? Well, we've got 2 more things, so we'll see if you believe after these last 2 things. Here we go. I need this and that. Or maybe I do need that. Oh no, you want me to use it? Okay. Okay. Here we go. Oop. Okay. Are you guys seeing? Do you see that pendulum? But do you notice that the pendulum, doesn't that seem reminiscent of a spring mass system?
Yes.
I hope you think so. Here's what I'm going to do now. I need to take this off and put this onto the bottom. Here, just a second. Okay. What I'm going to do is pour a bunch of salt into this Arrowhead water bottle. More than a little. Okay, there we go. Is anyone here? Is anyone here superstitious? Do you believe that if I actually get salt on the floor, I need to throw some over my left or right shoulder? Okay, well, I don't believe it, so. Okay, so now here's what I'm going to do. I'm going to set this in motion, and then, do you see this transparency that's under it? I'm going to move the transparency while the salt comes out, and boy, will you be shocked and alarmed when it makes a sine wave, which means it's simple harmonic motion. Are you ready?
How cool.
I agree. Here, just a second. I got to get this piece of tape off, but I can't let like all the salt fall out. Okay. Well, here, I better have another piece of tape ready or I'm gonna have a salt disaster. Okay. Alrighty, here we go. Here I'm gonna put it in oscillation. Here, is that going straight? Is that looking good to you guys?
Yeah.
Okay, now here we go. Whoa.
Wow.
That look like sine wave to you guys?
Looks like McDonald's.
Here, let's try it again then. Whoops. Here, I'm going to try pouring this back in here. There we go. I got a lot of it in.
15
A leak as well. Okay, here we go. Just a second. Let me.
just some sugar. Oh.
Sugar. Okay, here we go. I need to make sure it's going up and down pretty, pretty vertically, Okay, are you ready? Here it comes. Now, isn't that better? That's very sine wavy. Are you convinced now that this is simple harmonic motion?
Yeah.
Well, I've got a third thing to show you, but first let me close this off so I don't get a salt disaster. Although it'd probably be pretty smart if I emptied it right now, but I'm not that smart. Yeah, just so. Well, I got salt everywhere.
Did this happen for your last 2 periods?
I actually didn't do this the last 2 periods. I didn't have it set up, but I decided with you guys I would do it. Okay, well that was fun. Okay. Here comes the last attribute of simple harmonic motion. We had a lesson where I talked about the attributes of simple harmonic motion, and one of them was a displacement versus time graph gives you a sine wave, which you saw, and another one was one component of a uniform circular motion tracks simple harmonic motion, and then the third one is that for simple harmonic motion, the restoring force has to be proportional to the displacement. For simple harmonic motion, restoring force must be proportional to displacement. And I'm going to put a little space between 2 and displacement. This is what tells us, F equals negative kx, Hooke's law. And it's a restoring force because the force always wants to return the spring mass system to equilibrium. Well, the same thing happens with a pendulum. Let's say I have my pendulum right there. My pendulum of length L. And then I decide to displace my pendulum an angle theta. So I've displaced my pendulum an angle theta. This length is still L from there to there. There's 2 forces on this bob of the pendulum. The 2 forces being gravity, mg, and tension, T. Now, this pendulum is actually rotating, right? This ball is rotating about this point here. That's my point of rotation. So my pendulum wants to be restored to equilibrium, but it's not being restored by a restoring force, it's actually a restoring torque. I am rotating the pendulum so it will return to its equilibrium point. But if I displace it this way, then the torque wants to rotate it this way. If I were to displace the pendulum this way, the torque would want to bring it back to its equilibrium position. So I just want you to see it's a restoring torque. And I'm going to demonstrate that the restoring torque is proportional to the angular displacement. So this is a simple harmonic thing, but it's actually restoring torque that's going to be proportional to angular displacement. But it still works just fine. So let's go for it. I want to find my torque. Well, to find torque, I've got to do force times lever arm. Oh, is the tension making any contribution to the torque?
No.
Yeah, no way, because the tension, the line of action is passing through the point of rotation. This is like you running into the door and getting a black eye. You're not going to open the door with that force tension, but you are going to open the door with gravity, so I need to draw the line of action. So here's my line of action. And then I need to draw the segment from the point of rotation perpendicular to the line of action, which is right there, and that's my lever arm. This is the force, this is my lever arm. Now, someone who's an engineer would have probably looked at this and went, well, that's your lever arm right there. And it is. But you know, both of them are the lever arm, it's fine. And I hope you see that this lever arm is going to be L, the hypotenuse, times the sine of theta. So L is going to be big L times the sine of theta. So now I get an expression for the torque. Torque is going to equal force times lever arm. And so the torque is going to be the force mg multiplied by the lever arm, which is L sine of theta. And this is a restoring torque because it's restoring the pendulum back to its equilibrium position. If you want, you could put a minus sign there if you're so inclined. This is a clockwise torque after all. But here's the issue. Do you notice I do not have my torque being proportional to angular displacement. My torque is proportional to the sine of the angular displacement. So I don't get to claim simple harmonic motion yet. But there's something special I happen to know about the sine of an angle theta and the angle theta itself. This is something you guys learned about in calculus. You learned it in August, which means you have no recollection of having done it.
That's true.
But you did this, and you may have encountered this with your L'Hopital's rule stuff. The limit as theta approaches 0 of the sine of theta over theta. Do you guys know what that is? Yeah, it's 1. Good for you. Oh my God, I wish you were in my class. 1, yeah, it's 1, right? That is, for small angles, theta and sine of theta are approximately the same. Okay? You can do this on your calculator if you're in radians mode. Just go 0.1 and then go sine of 0.1. And you'll see the sine of 0.1 is really close to 0.1. Or the sine of 0.05 is really close to 0.05. In fact, you know, I could actually do this. Theta in degrees, theta in radians, and then the sine of theta. I can actually make a chart comparing them. And you find that theta in radians is really close to the sine of theta. Like, if my theta was 5 degrees, then, here, I'm going to get my calculator. Just a second. Okay, 5 degrees is approximately 0.0873 radians. And when I take the sine of 0.0873 radians, I get 0.0872. That's 0.1% error. So at 5 degrees, sine of theta and theta are pretty much the same. Or how about 15 degrees? This would be 0.262 radians. And the sine of it is 0.259. So again, this is approximately 1% error. Okay? 3 parts out of 260. I could even go as far as 30 degrees. 30 degrees is 0.628 radians. And of course, the sine of 30 degrees is 0.5. Wait just a second. Oops, I messed up. 0.524. And this is 0.500, of course. And so that's going to be around 5% error. Okay? So you see, for angles below 30 degrees, your theta is approximately equal to the sine of theta. So I'm going to actually make that substitution. I'm going to say for small angles of theta, for small theta, theta is approximately equal to the sine of theta. And so I'm going to make that substitution. And now I've satisfied my third requirement for simple harmonic motion. That is, I've got a torque proportional to the angular displacement, a restoring torque proportional to angular replacement. So I can actually write that down. I can go, yay, I have simple harmonic motion. But with one proviso. What has to be true about the angles? Yeah, what happened? The light's on. Here, do you want me to turn? Yeah, just turn the light off. But is it still recording? Yay. Okay, I have simple harmonic motion only for small angles of oscillation. Because that's the only way I get a restoring torque proportional to a displacement. So what I'm saying is, when you do your pendulum lab, okay, when you're measuring length of pendulum and getting period of pendulum, you need to have an angle of oscillation that's something like this, right? Something that's reasonably small angles. Please do not give me angles of oscillation that look like that, because this isn't going to be simple harmonic motion anymore. Not gigantically huge angles, you know, of theta. It's got to be reasonably small angles of theta. You guys okay with that? Or you're not going to have simple harmonic motion. Okay. Well, now are you convinced that a pendulum is simple harmonic motion? Have I beat you into submission? Yay. Good. Then let's go ahead and derive this formula. Let's go ahead and derive omega equals the square root of G over L. And yesterday, I started with force equals, force equals ma. Today, I'm going to have to start with torque equals I omega. For my torque, I've got my torque right here, negative mg L theta. I can get my rotational inertia because a pendulum is pretty much a point mass at the end of a massless string. And I want to remind you that if I have a mass m rotating a distance r away from a point, away from the point of rotation, then the rotational inertia is mr squared. We learned that in chapter 8. And so in this case, the radius, the distance from the point of rotation is L. So it's going to be ml squared times alpha. And now that I've hopefully convinced you all that this is simple harmonic motion, that means I get to do this thing. I get to relate theta, you know, the angular displacement, the angular velocity, and the angular acceleration with the cosine omega t, because it follows circular motion. So theta equals cosine omega t, omega equals negative omega sine of omega t, and then alpha is going to equal negative omega squared cosine of omega t. And I'm just going to make those substitutions now. So I got negative mgl cosine of omega t. Here I've got ml squared times alpha, which is negative omega squared cosine of omega t. Okay. Looking at these two sides, what do you notice cancels? What's that? What's that? Good, one of the L's. This is L squared, that's L, so boom, boom. What else cancels? The mass. Yeah, the mass. And that's actually really important. Do you notice the mass cancels? I'm essentially telling you I'm going to get an equation for the period and frequency and angular frequency of a pendulum, and mass is irrelevant. How many people here have had the experience of going on a swing set with a brother or a parent who's significantly different in weight from you? I do that. I used to do that with my daughter and my son. And when my cute little daughter and my cute little son, back when he was a cute little son, you know, we would swing together. And guess what? We would swing together. We'd have the same period, even though I was 5 times their mass. We would have the same period. We would just swing together. Why is that? Because the period doesn't depend on mass. So I get to have the same period as my daughter. We get to swing together. And then finally, the negatives cancel and the omega, cosine omega t's cancel. Okay? And so the left side, I'm just left with g, and the right side, I'm left with L omega squared. So I got omega equals the square root of g over L. And there it is. That's my formula for the angular frequency of a pendulum, as long as I oscillate at a small angle. And since omega is equal to 2 pi f, I can say that frequency is equal to 1 over 2 pi times the square root of g over L. And because frequency is equal to 1 over t, I can get the equation that our textbook loves and that the AP exam people love, which is period equals 2 pi times the square root of L over g.
Yeah.
And that's the equation I'm going to use. Yes? Sure. Okay. So is that good for you guys so far?
Wow.
Because now it's time to do some problems and then we're done. Yeah, pretty long, but I hope you're convinced. Like I said, I hope I beat you into submission. Okay, so here comes the example. Example number 1. I want a pendulum of period 1 second. Find the length. Please do this problem now. What length pendulum is going to get me a period of 1 second? So which guys get me? What's that? 0.25?
Yeah.
Good. 0.25 meters or 25 centimeters? Here, let's go ahead and demonstrate that right now. I'll use this guy. I need to first get this guy to have exactly a length of 0.25. So here's, 25 centimeters is down to there. So I go, by the way, what am I going to measure to if I have a bob, if my pendulum isn't a point mass, but it actually has some size to it? How am I going to get the length of my pendulum? What should I measure? What's that?
The center of mass.
Yeah, I'm going to measure the center of mass. Thank you very much, Noah. Thank you for being so cool. So I'm going to estimate what the center of mass is. That's a bit high. Here, let's go with that. Wait, I went the wrong direction. Stupid thing. You'll be better off than I am. I can't even figure out what I need to do. I need to raise this a little bit. So, okay, that's about right. Okay, so I'm about the center of mass. Does someone have a phone? I'd like you to time this. Who's got a phone out? Who's gonna be the timer? You have a phone out, Alejandro. Let's use your phone. Go to clock, go to stopwatch. Clock, stopwatch. Okay, great. So here we go. This period should be 1 second. So I'm going to have you do 10 periods. And of course, how many seconds should 10 periods take? So yeah, 10 seconds. So tell me, where are you going to clicky? Are you going to clicky here or clicky there? Okay, good. Then please shout out clicky when you clicky.
Clicky.
1, 2, 3, 4, 5, 6, 7, 8, 9, and what'd you get?
Oh, 10. I thought you were going to say 10. So
Oh no, I was waiting for you. You have to be the one clicking. Okay, let's do it again. Because it's you who's got the rhythm. So we want none of that delay time, reaction time when I say something and for you to act. So here, go ahead and just say clicky.
Clicky.
1, 2, 3, 4, 5, 6, 7, 8. Get ready. 9 and
Clicky.
what'd you get?
10.77.
10.77 seconds. So that's 8% off. Oh, that's not that great, but that's okay. So if someone ever kidnaps you and they lock you in a room with no clock and all you have is like your shoes with the shoelace and you want to keep track of time, you can always make a pendulum that's about 25 centimeters long and each period will be a second. Oh, I don't know if that makes you feel better.
That's what you do, I guess.
So let me ask you this, okay? We found that the length was 25 centimeters for a period of 1 second, but what if I wanted a period of 2 seconds? I want to double my period. What am I going to have to do to that length in order to double my period? How many people here say, double the length, I double my period? How many people say, quadruple the length and I double my period? Okay, good for you guys. Tell me, Sean, why did you say quadruple the length? Thank you, because you have to take the square root of it. If you double your length, you're only going to be increasing your period by a factor of radical 2, correct? So I want you to see that if I want 2 seconds, I'm going to have to quadruple the length to double the period. Because, we're getting the square root of L. Okay? Let me ask you another question. How many people have seen a video of astronauts walking on the moon? Okay, there's video of that. You've got the astronauts walking on the moon. And now normally if they want to get from point A to point B, they hop, because the gravity is so low on the moon. So go hop, hop, hop. But if you ever see them just walking normally and having their arms swing normally, have you ever noticed that their arms tend to swing pretty slow? And if they walk, they tend to walk pretty slow. Now they can make their arms move faster, but if they're just moving naturally, their arms and legs tend to move pretty slow. Could someone tell me why? Why would their arms move slower on the moon than here on the Earth? Here's my arm. Here's the way my arms normally swing. When I walk, the rate at which my arms and legs swing when I walk is determined entirely by this formula. My arms and legs are just pendulums, and they have a natural frequency, and they swing at that natural frequency when I walk, right? So why do the astronauts' arms and legs swing slower when they're on the moon? Yes, Fatima. Thank you. Because G is smaller. Since G is smaller, what is that going to do to the period? Yeah, it increases the period. Because where is G in the equation? Yeah, in the denominator. So a smaller G in the denominator makes a bigger value. It makes T bigger. So yeah, astronauts are going to have bigger periods of oscillation for their arms and legs because they're in an environment with a smaller G. Let me ask you this question. Suppose all of us went to Jupiter. where the acceleration of gravity is 20 times that of Earth. Now how are our arms and legs going to swing?
Like car wheels.
Really fast. Yeah, until we fall to the ground, crushed by the gravity. But until that happens, man, we're swinging fast. Okay. Well, hey, does anyone have any questions or issues on this? Because, that's it. That's all I got. Are you convinced that pendulums are simple harmonic motion?
Yes.
Good. Tell me, when you do your lab, what has to be true about the angles of oscillation? Small angles. Okay. How many people have gone to Griffith Park Observatory? Have you seen their Foco pendulum?
Yeah.
The thing that swings back and forth. What do you notice about the angular displacement of that Foco pendulum? Is it big angles? Heck no. Very, very small angles. Okay. Bye-bye.